Okay, so for your next part of your heat transfer of heat chapter, we're going to talk about the methods or the types of heat transfer. So first one we're going to talk about is your conduction over here. Now basically it's the transfer of heat, if you don't want to keep writing the word thermal energy, is without a flow of any medium itself. So basically what this means is that this medium can be your solid, liquid or gas, is that they will not actually move. They will just vibrate about their fixed position itself. They won't actually move from place to place. So most of the time, when we talk about conduction, it's mostly in solids, but conduction can still take place in liquids and gases as well. So what happens here is that, first thing, you have a Bunsen burner. What happens over here is, step one, you gain heat first. Okay? What happens is when you gain heat, you will have more kinetic energy. More kinetic energy, you will move fast, move more vigorously. Kind of like what we did previously in your earlier parts for your expansion, right? So same thing, you gain heat, you will move more vigorously. So when you move more vigorously over here, what happens is that you will collide with neighbors. Okay? So when you collide with your neighbors, what happens is when you bump into them, you will actually transfer heat. Okay? So you will transfer heat from hot to cold. So what happens at the end is that basically all of them, your whole metal, it becomes same temperature. Okay, so what happens is that eventually you'll reach same hotter temperature. Okay, so you'll constantly gain heat, gain heat, gain heat, gain heat, bump into your neighbors, transferring all your heat. So what happens is that at the start, you gain heat, only these molecules will vibrate more vigorously. And what happens as they keep bumping along, bump along, bump, more and more, they will slowly transfer all of their heat from the hottest to the coldest part until every part of your circuit itself, all of them are all hot 20 degrees Celsius over here. So in this case, this is how it actually works. Okay. So down here, you can see the methods are exactly the same. So first thing, you gain heat, you have more kinetic energy, you vibrate more vigorously, you collide into your neighbors, you transfer your heat, and what happens? You will reach a new equilibrium temperature that is actually hotter than before. Okay, so a lot of steps in this paragraph over here, but basically it's almost identical to what we did just now. You basically gain heat, you have more energy now, so you move more vigorously. Since you move more vigorously, it's like you have a lot of energy, you have nowhere to spend. And what happens when you try to fidget about, you actually bump into your friends, you collide with your neighbors, and you actually transfer the heat from hot to cold, and you eventually reach the same temperature. So so you can see over here, sorry, you see over here, you started with 120, so eventually this will slowly increase until it's 120 degrees Celsius. Okay. So, and if you notice, basically, these particles, they do not move. Okay. It is only the heat that is moving from hot to cold. The particles themselves, they are actually remaining in the same original position. So because of that, they are not actually moving. They are just moving about their fixed position. They are just vibrating about their fixed position over here. Okay, so just be careful. This is how it works. So basically, very long paragraph and a few points you need to take note. Gain heat, move more vigorously, collide with neighbors, transfer heat from hot to cold. Same temperature at the end. Okay, so let's see if we can make this shorter for some of you. Okay, let me try to make it even shorter. When you gain heat, you move more vigorously. You transfer heat upon collision. Then heat transfer from hot to cold. reach higher temperature. Okay, so something like that. Or transfer heat from hot to cold until same temperature. I think this would be better. So okay, so a little bit more concise. So really depending on your school itself, you might need to actually phrase it differently. But basically the gist of the idea is you gain heat, you move more vigorously, you transfer your heat when you bump into your neighbors or when you collide with your neighbors, and you will transfer your heat from hot to cold until you reach the same temperature. Okay, so that is for your conduction, how it works. So this entire long paragraph or the points that you see here, right? This is only when they ask you to describe how conduction takes place. Okay, occurs. So this one, most of the time, it will actually be a 2 mark to 3 mark question when they ask you to describe how conduction takes place over here. So 4 points to take note of to get your 2 to 3 marks over here. Gain heat, move more vigorously, transfer heat upon collision, heat transfer from hot to cold until same temperature. Okay, this one is much more concise, so just use this one. Just use your own words to explain, but I need to see all of these keywords over here. Okay, so this one is the sample, and basically the keywords are as follows over here, all these 4 points. Okay, so now when we talk about your heat transfer itself, we're going to talk about your rate. How fast or how slow is my heat transfer? Okay, so normally when we talk about how fast and how slow itself, we are actually talking about fast. We are talking about good conductor. Slow, we are talking about poor conductor. Okay, good conductor of heat, poor conductor of heat over here. Okay, so your rate depends on your material. So if you're talking about metals, now metals are all generally the best conductor of heat, or it's one of the best conductor of heat, and it is because they have free mobile electrons. Okay, so what happens is basically inside this diagram over here, okay, I'm gonna sketch another one out. So typically all of them look something like this. They should be more closely packed together. So what happens is in between all your metals, there's actually a lot of electrons that are just floating about. So what happens is when you gain heat, you vibrate, these electrons also gain heat. So what happens is that these electrons can actually move directly through the gaps all the way to the colder part. Okay, so they can actually transfer your energy much faster compared to just particle vibration. So because of this extra free mobile electrons, you can actually conduct heat faster. Okay, and next comparison is that we're going to compare solids versus liquids and gases. Okay, so if you think about it, solids, they're all very closely packed together. Okay, compared to liquids and gases, this is solid. For your liquid itself, they are still somewhat loosely packed together. And then for your gas, they are very far apart. Now remember, conduction takes place through vibration. So which means your particles must be close enough to actually collide with their neighbors. So if your liquids and gases, or your liquid molecules and gas molecules, they are very far apart. This also means that they can't actually bump into each other more easily, so they cannot transfer heat as easily as compared to solids, which are very closely packed together. Okay, last but not least, porous materials basically means that they trap air. And first thing, air, because it's a gas, is a poor conductor of heat. So because of these materials that actually trap air, they are also very poor conductors of heat. That's why normally all your winter clothing itself, whether it is your jackets or whatsoever, what they're actually doing is trapping the heat around your body, so it serves as a layer of insulation. So because of that, you will lose heat slower. Remember, when we talk about poor conductor of heat itself, you actually want to say you lose heat slower or you gain heat slower. Okay, basically, if you are poor, we are talking about slow. Okay, if you are a good conductor, on the other hand, you will gain faster. So just be careful which is which. Okay, the phrasing will be slightly different. Next, let's talk about your difference in temperature. Basically, as long as you have a big difference in temperature, when you have a very hot to cold, it will be very fast. But let's say you are from not so hot to cold, you'll be slower. You'll still be fast, but not very fast compared to the difference. So just take note, when you have a very big difference, it will take place faster. Because the world doesn't like to be different, so it will always try to have some form of control over what is actually going on over here. Okay? So surface area, because conduction requires your molecules to actually touch one another, if you have a very hot object, let's say like my cup of coffee, and you have your finger that has your molecules inside. What happens is, basically, if you poke it with your finger, only this part will gain heat first. But if you use your entire hand to grab this hot coffee, for example, you use your entire hand to grab it. Okay? So what happens is, all the parts that will touch the coffee will gain heat. So the larger the surface area, the more heat that you will gain. So you'll gain heat faster if you have a larger surface area. Okay, so as your area increases, your heat gain faster. Okay, so do take note about this. Now, for your applications, first thing, trap, as I said, is very, very good at having poor conductor of heat. Okay, poor conductor of heat. So the thing is, you want to slow down. Slow heat transfer. Okay, so can be gain heat or lose heat. You just want to slow down the heat transfer. So the thing is, when you wear fluffy clothing itself, first thing, usually when we are wearing winter clothing itself, your surroundings is cold. So what happens? The person himself is hot. So what happens is he's losing heat. So the thing is, if you want to keep warm, you don't want to lose heat so fast. You want to lose heat slowly. So if you lose heat slowly, you need a poor conductor of heat. So what happens is that you will actually wear winter clothing to actually trap the heat around you. So you lose heat slower. Now for double glazing over here, those are for windows. And basically double glazing means that you actually have a thin layer of air between the two layers of window. This is window 1 and this is window 2. So what happens is, basically, if some of you have sat in airplanes before, you'll notice that in airplanes, sometimes you actually have this layer of protection itself that actually will have all of this in between, and therefore you will actually be able to protect yourself from all the different So when you see an airplane, first thing is, in an airplane itself, I don't know how to draw airplane, but airplane looks something like this. Okay, outside the environment is actually cold and inside is actually warm. Okay, so what happens? You are losing heat. So the thing is, you don't want to lose heat so fast because outside is very, very cold. So you want to lose heat slower. So by using this trapped layer of air in between all of this layer, this is all air. So this trapped air will be a very, very good, very, very poor conductor of heat. And because of the poor conductor of heat itself, you will actually lose heat slower. So that's why double glazing works. Then basically all of this example itself, they all trap air, and therefore they're all poor conductors of heat. So you just need to ask yourself, do I want to gain heat faster or do I want to lose heat faster? Then you will choose whether you want a poor conductor or a good conductor. Okay? So in the opposite sense, if you want to have a good conductor of heat, means I gain or lose heat fast. Okay, so you'll use it for cooking. Okay, and poor conductors like clay pot, right? Sometimes you see clay pot in cooking. They are all poor conductors of heat. So the thing is, if they are all poor conductors of heat, why do we use it for cooking? Because the thing is, it loses heat slowly. Because it loses heat slowly itself, food is kept warm longer. Okay, so because food is kept warm longer, sometimes you see clay pot, those kind of restaurants that cook clay pot dishes, they actually usually will cook it to quite a late time, because let's say some people want to hang out at night, they will do it like after midnight and stuff like that. So they are talking. But if you use clay pot to keep your food warm, you actually keep it warm for a very long period of time. So maybe when they talk all the way to like a few hours, the food will still be somewhat warm. Okay, and poor conductors also have a use in cooking as well, but now we are using it for the handles. So if when you use it as the handle itself, the thing is, because they are poor conductors itself, you will gain heat slow. You will actually gain heat slow and you lose heat slow. Okay, so what does that mean? If your cold hands, okay, you will lose heat slowly to person's hand. So if you touch it, you won't burn yourself if you are cooking your food, because normally your saucepan is very, very hot, right? So your handle might be hot. But if you touch it, the thing is, because the handles are made of poor conductors of heat, you will lose or you will gain heat slowly. Okay? So what does that mean? Your hand gains heat slowly from the handle. So you won't burn yourself. Because the reason why we burn ourselves is because we gain heat too fast to the point that your skin actually will get injured. So because of this, you want to gain heat slowly from your handle that is quite hot. Okay? And basically, factors, remember, conduction requires large surface area, right? So you want to maximize your surface area by having all these funny looking shapes. And inside the coil itself, you have all these funny looking shape. You are actually maximizing your surface area. So because of this, remember, more surface area means faster heat transfer. Okay, whether it's losing or gaining heat transfer. Okay, so because that, most of them, your kettle, electric kettle, your refrigerator, or your condenser, all of them will have larger surface area to actually speed up the process of gaining and losing heat. Okay. Next, let's talk about your second process. This is your convection. Convection is the transfer of heat from one place through the movement of medium. So this means that your medium itself must move. So they must have some form of motion itself. So this one only means liquids and gases. Why? Because solids cannot move. Solid particles have very strong forces of attraction. So because of this, this also indirectly means that they can't actually move itself. So convection can only take place in liquids and gases. And the thing is, density is very important. So do take note about your density. Remember, density is mass over volume. So in this case, we're actually going to talk a lot about density in this part. So over here, this chunk is when they ask you to describe how convection takes place. Okay, so let's break it down over here. First thing, you have this heater over here. So what happens is that the air here will gain heat. Okay, so number one, you gain heat. So when you gain heat, what happens? You will expand. Volume increase, and your density decrease. So when density decreases, your hot air rises. Okay, so when your hot air rises, what happens? Cold air, which is now denser, will sink down and they will actually come and replace it. So what happens is there will actually be a two-step process. So your hot air rise, your cold, cooler, and denser air will sink. Okay, so what happens? They will sink to replace them. So what happens? Because when your hot air rises and it moves up, right, there's an empty space. There will be an empty space over here. So what happens? Your cold air will actually come down to replace it. And when your cold air comes here, what happens? It gains heat, it will rise, and then what happens? Your cold air will sink, and basically it will just keep forming a endless loop. This circular cycle is what we call your convection current. So last but not, cycle repeats to form convection current. Okay, so unfortunately, this one is a little bit long-winded. So do take note, steps. When you gain heat, expand, density decrease. Okay, part one, part two. So what happens? Hotter will rise up. Your one will cool down, replace it, and cycle repeats. Okay, so you can see all the different steps. Step one, step two, step three, step four, step five. Okay, give me a second. Let me see if I can find the picture which I made for one of the students. I believe it is this. Okay, so basically, this is the one that I wanted to mention. First thing, now I have a picture down here so you can refer to it as well. So first thing, you have a Bunsen burner and a beaker sitting on top of a tripod over here. So what happens? You first gain heat and you expand. Now in part two, as volume increases, density decrease. So your hot and less dense water will rise up. Once you hit the top, there's a ceiling, right? So they actually move to the side. So what happens? Cooler and denser water at the top will actually sink down directly downwards to replace your hot water. And because they will curve back to the middle, so what happens is they will gain heat over here, the cycle repeats to form convection current. So if you can, this one is a much clearer way to phrase your answer. So 5 points, write it in in the space below here. If you have the space, if you need to, you can draw the drawing as well. But basically, you should put it inside your notes as well. Sorry, give me a second. Okay, so if you can, in the space at the side or at the top here, you can write it here as well, or you can write in the space below. Not much space that is here, but try to fill it in as much as you can. Okay. Right, so basically it is your 5 steps, just that it's a little bit more in detail, but basically the gist of the idea is all there. Okay, hot air rise, cold air sinks to replace, and then cycle repeats to form a convection current. A lot of students actually miss out the to form convection current, so do remember that this circular cycle is what we call your convection current. Okay, so the thing is, what affects your convection current itself is your basically this one. This chunk is just saying temperature difference. Okay, so the larger the temperature difference, the bigger the change in your how fast convection will take place. Now, typically for convection, they are mostly asking about how it works. They rarely ask about how fast or how slow convection is, unless they are actually comparing about this one. Okay, this one is basically liquid versus gases. Okay, so before we move on to that, let's talk about viscosity. This is how thick the liquid is. Okay, so normally liquids which are very thick, like soup or honey, they don't flow very well. So because of that, we don't use them. Okay, we usually just use your air and your water. So most of the time, we are just using air and water. That's it. Okay, this is just the reason why. Because if they are so sticky, basically they can't move very well. So because they can't move very well, that's why normally if you try to cook caramel, if some of you tried it at home to try to cook your own caramel, you actually take a much longer time to actually cook caramel. So because of that, it is not advisable. So for this one over here, we know that gases expand more. Remember, gases, when you actually expand, is because gas have weak IMFOA. Okay, so because of that, you will expand more. You expand the fastest out of the liquids and gases. So because of that, you expand more. What happens is that you also have the, okay, you expand more, you also have the greatest change in density. Remember, then density is mass over volume. So if your volume increases a lot, your density also decreases a lot. Okay, so because of this, density drops a lot. So what happens is that your convection current form very quickly. So because of that, you actually form convection current much more easily. That's why normally if you want to cool down a house, aircon is much faster compared to fans. Okay, that's why normally aircons are in almost all households in Singapore. But basically, that's how it works. Okay. Now, for applications wise, sometimes you'll see your kettle over here. If you draw a kettle that looks something like this, normally all the heating coil itself, they're actually found at the bottom. Why? Because when you have water, you want to gain heat, expand, you want to have a very big convection current. Because if you actually place your kettle, the heater of your kettle at the top, okay, let's say you place it at the top here. What happens is all the water at the top, it gains heat and expands. The convection current that they form is only so small, which means that this bottom part of your liquid, there is no convection because your convection current doesn't touch that part. They only heat up the top part over here. They only heat up this part. So because of that, there's no convection. The only way that you gain heat is conduction. But water is a poor and very poor conductor of heat. So what does that mean? You gain heat very slowly. So because you gain heat very slowly itself, basically it doesn't actually, your conduction is very slow. So this one, no matter how much you keep heating it up, this part doesn't actually gain heat very fast. It will be very cold at the bottom. Okay, so it's not good for if you want to boil water. All right. So all your aircons, I'm pretty sure all of you have seen aircons before. All aircons are actually found at the top of the ceiling, or they are actually at the sides of the ceiling itself. And for your fridge, most of the time, some of the, especially the older fridges, usually the ice cubes are all found at the top because you want to cool down the top. So what happens is actually the reverse. First thing, let's draw your fridge. Now, if your fridge looks like this, what happens is you have a cooler at the top. So what happens? The air at the top cools down. Cool down, you will contract. Your density will increase. You will sink down. When you sink down, what happens is that hot air at the bottom rises. So what happens when you go to the top? Cycle repeats. Convection current form. Okay, but this is now your cooling convection current. So in this case, first thing you cool down, you move to the side. What happens that your hot air moves to the top, it gets cooled down and the cycle repeats. So what happens? You will cool down your fridge very easily itself. Okay, so basically this is the opposite of what we mentioned here. Basically, this is a heating convection current. This is a cooling convection current. So cool down, contract, density increase, you sink down, or air rise, cycle repeats, convection current form again. Okay, so if you want to increase your convection current, this is what you're supposed to do. This is increase. On the other hand, this is for you to decrease convection current. Okay, so the thing is, sometimes you have a cup of hot coffee. You have your coffee and you will have hot air at the top gaining heat, and you form your convection currents cooling down your coffee. So you don't want that to happen. So all we can do is you can place a lid on top. So what happens is at this point, all the hot air that tries to escape can very small convection current, they are all trapped at the top. So you will lose heat very slowly to your surroundings compared to just now, where you have your cup that is open. All the hot air will just rise up and you will form convection currents cooling your hot water very fast. Okay, so just take note of all this. And if you notice your fridge, in your supermarket, your fridge, right? Sometimes they actually open from the top. So your ice cream drawer itself, they can actually move down. So what happens is inside you have all your ice cream down here, right? So the thing is, cold air sinks, which means outside, which is hot, they won't go in because hot air will rise. So you can actually leave your ice cream compartment open, so you can actually don't need to actually close it. The reason why we actually close it is because there might be thieves. So because of this, if you have cold air, the cold air can only gain heat via conduction. Okay, you can only gain heat via conduction, which is very slow because air is a poor conductor of heat. Okay, so it's actually not very good. So examples, thunderstorms, sea breeze, land breeze. First thing, during the day, this is the land, this is the sea. During the day itself, the land itself will always gain heat faster, so this is hot air rise. Okay, so hot air rises, what happens? Cold air from the sea will blow like this. So what happens? This is your convection current that is formed. Hot air rise, cold air sinks, and you will feel the cold air blowing to your face. But at night, what happens is that the sea is actually warmer than the land itself. So hot air rises, cold air sinks. So what happens? You actually form a convection current. So the wind will be blowing behind your head. So next time, if you all actually go to a East Coast Park or whatsoever, you all can always go and check on the direction of the wind blowing against your face. So you know whether the land is hotter, or you can check if the sea is hotter because of the direction of the wind blowing towards your face. Okay? All right. So next one, last but not least, let's talk about your radiation itself. Radiation is a bit special. Usually it is through electromagnetic radiation. So usually we will just say it is through infrared radiation. All right. So don't worry too much about some of this over here. Basically, it is this part. All right. I will summarize it to you. So for radiation itself, we don't actually use gain heat or lose heat. When you lose heat, we actually say emit radiation. Then when you want to gain heat, we will say that you absorb radiation. Okay? So all you need to do to ask yourself is, do you want to gain more heat or lose more heat? Do you want to emit more radiation or absorb radiation? So let's say my favorite cup of hot coffee versus a cold cup of coffee over here. So what happens is, basically you are losing heat over here, right? So this emits radiation, and my colder cup will actually absorb the radiation that was emitted. Okay, it's always from hot to cold, regardless of whether it's conduction, convection, or radiation. It's always going to be from hot to cold itself. Okay, so because of this, this is how it works. And in most cases, radiation, we are actually more interested in your factors over here. So color and texture, your surface temperature, and your surface area over here. These few are the ones that you're more interested in. So basically, black and matte. When we say matte, you mean dull or rough, versus your polished and shiny surfaces over here. Now, when you are a poor, or if you are black, you are actually a good absorber or good emitter of radiation. So what does that mean? You will, good absorber, you gain heat faster. If you are a good emitter, you lose heat faster. Okay? And with your white and polished surface, let's use a different color. White and polished surfaces, they are poor absorbers and emitters of radiation. So what does that mean? You will gain heat slower, and this one you will lose heat slower. So depending on the context of the question, you might want to use different materials over here. Okay? So black can, you heat up faster because you gain heat faster from the sun. Then your black can, similarly, will cool down faster because you lose heat faster because you are at room temperature. So it all depends is, ask yourself, is my object, the black can, hotter than the surroundings or colder than the surroundings? Because normally if you are cold, you are gaining heat. If you are hot, you are losing heat. Okay, so do take note about all of this itself. So surface temperature, like I said, when you have a larger temperature difference, faster heat transfer. This is true for all three methods. Okay, so as long as your temperature difference is very, very big, you have this. And basically, if you notice, all of your radiation takes place by your surface area. So if you emit all your surface area, it's very easy for you to emit radiation compared to if you have a small surface area. You can only emit a little bit compared to your larger surface area. So just take note, it's all due to surface. Okay? So applications wise, if you all notice, when you want to transfer heat slowly, we will use all of these, which are poor emitters or absorbers of radiation. Okay, so in this case, most of our houses, they are all painted white. Why? Because you want to reduce the absorption of radiation to keep your house cold, especially in Singapore. That's why normally you don't really see black walls, you don't really see black houses. It's actually to keep our house warm, cooler, not warm. It's really very hot in Singapore. Okay, then for y'all, sometimes you will have reflective walls, is you absorb less heat, and then at night radiate. Shiny reflective falls are all poor absorbers and poor emitters of radiation. So they will actually absorb less and emit less as well, so that your house is not so bad. In some cases, when there's disaster, okay, disaster victims, so what happens is, because they are caught in snow, they are losing heat very fast. Okay, it's so fast that they are almost gonna die. So what happens is that you don't want to lose heat faster. So you want to lose heat slower, right? So you'll use a shiny blanket. Okay, we'll use a shiny blanket. First thing, why a shiny blanket? Okay, ask yourself, you have your three methods: conduction, convection, radiation, right? So conduction, convection, radiation. You can actually use all three methods to explain. So first thing, conduction, your blanket itself, it will trap air, which is a poor conductor of heat. Okay, so you'll lose heat slower. Next, your convection, because you trap air, no convection. So you don't lose heat by convection. Last but not least, radiation itself is a shiny blanket, so it's a poor emitter of radiation. So which also means I lose heat slower. So can you see, using all three methods, 1 mark, 2 mark, 3 mark, or even 5 mark questions, basically you have actually explained, okay, because I don't want to lose heat so fast, I want to lose heat slower so this person can warm up, right? So I use a shiny blanket. Conduction, because a blanket will actually trap air, so you will actually gain heat slower. Lose heat slower, because this person is still hotter than your cold surroundings. Then if you talk about convection, because you actually trap the layer of air, air cannot move. So because air cannot move, there is no convection that takes place. And for your radiation itself, because the outer layer is shiny, it's actually a poor emitter of radiation. So this person, he's emitting heat slower. So he's losing heat slower, so he will survive. He'll warm up and he won't cool down and he won't die. Okay? On the other hand, this is a heater, a solar heater. Okay, this is a solar heater, and how it works is all of these pipes, they are all black. So black pipes are all good absorbers of radiation. So what happens is they'll absorb heat from the sun, and they'll actually heat up the water that's flowing through these pipes. And if you notice the back, these are all shiny surfaces so that they will actually absorb less heat from the sun, and they'll actually reflect them towards the black pipes. So your black pipes will actually absorb more heat from this reflection as well. So because of that, the water inside this heater will actually become quite hot inside these pipes over here. Okay, so do take note about all of this. So now that we learned about your conduction, convection, radiation itself, all we need to do is sometimes just ask ourselves, first thing, if you have a bonfire, ask yourself, number one, does it touch you directly? Okay, if answer here is yes, then this is conduction. If it's no, let's move on to number two. Does the hot air touch you? Okay, if the hot air touch you, yes, this is convection. If it's no, it just means it's radiation. Okay, so how do we know this? First thing, air at the hot fire will gain heat, expand, rise, density decreases, right? So you rise up to the top. So first thing is it rise up to the top and cold air will try to come in to replace it. So first thing, is this person touching the fire? It's not. So it must be number two. First thing, is the hot air touching him? No, it's actually the cold air that is blowing towards him. So why does this man still gain heat? It is because of the radiation from the heat itself. So this is actually your radiation. So this man, like for example, some of you might eat barbecue, Korean barbecue. You all sit near the charcoal itself. You might actually feel heat blowing towards you, but that's actually your radiation that you actually absorb from the very much hotter charcoal or fire that you have in front of your face. Okay, so do take note, basically we have covered your conduction, convection, and radiation over here. All right, so just be careful. Most of this chapter, especially conduction, convection, radiation, they are very heavy on explanation or heavy on description itself. So I need to see certain words. If whenever you see good or poor something, it's actually asking you about how fast and how slow. If you talk about your conductor of heat, is actually talking about conduction. If you want to talk about radiation, you need to use the word emitting and absorbing. You cannot just use whatsoever. For convection, unfortunately for us, we need to kind of memorize how you are supposed to actually describe your convection currents, your 5 keywords, they all must be there. So if you miss out certain keywords itself, you actually lose marks because of this. And especially convection is very, very, very commonly tested. So you need to be very familiar with this explanation. And for your conduction itself, usually it is asking you poor conductor heat, so what? Lose heat slower. Okay, or they'll compare your radiation. You have a black surface and a white surface. So what's the difference? Black surface is a good absorber of radiation. You'll gain heat faster than a white can, which is a poor absorber of radiation, something like that. Okay, so with that, that will be it for your heat chapters.